Okay, we can get started. Good morning. Was the tutorial on fuse useful on last Friday? Right? No? If you have any, I mean, I'll be back in town for another 2 weeks at least. So if you have any question over the Easter break, send me chat or email. Right? So what was your concern? Was it clear, not clear how to use it, or it was fairly straightforward? Regardless, right?
It was straightforward, but he didn't really know what we need to do for the project. Like he taught us about fuse, but he didn't say, make this, make a main program that's going to do set up your file system this way, or.
Okay. So he went through the null example, right? Null or hello.
Yeah.
So if you look at the directory, the fuse example directory, there should be a fuse exmp _ some file, right? That should be a good startup point, right? So if you look at that file, so essentially what you're looking for is there'll be I forget what the exact name is, something main program, right? Which you have to call, right? And then there'll be one structure with a whole bunch of fields, right? For open, close, what have you, right? So you can ignore everything else about the hello thing. All you have to do is, for example, for the open one, you have to put in your piece of code, right? And that's all you need from the fuse component, right? And after that, you need to figure out how to mount and unmount all those things which he went through, right? Your code will go in where if you have an open functionality, you'll put it there. If you have closed functionality, you put it there, right? And that's it, right? So you can ignore everything else about the hello program, and same for the fuse example program, right? It'll have all the system calls listed on the structure. Just replace each one of them with whatever your call is, right? So the role that fuse plays is very minimal in terms of how much code you have to add, because essentially you have to say, for open, you call my function, for close, you call my function, and so on and so forth. But fuse is the way that you see your program. So in that sense, if you don't get fuse to work, then you can't interact with your program. But in terms of fuse programming, the only thing you do is change the structure and call fuse main, and everything else works for you. Yeah.
So the project goal is to implement those syscalls for the past.
Yeah. So the more you implement, the better your file system is. The less you implement, it doesn't have much functionality. And I leave it to you on how complex you want the stuff to be, right? Right. So the fuses should not be the part where you get stuck, right? You may run into some problems, but that should purely be a syntactical issue of, are you compiling properly? Are you invoking it properly, and all those things, right? And one of the things when you operate with the fuse and all those things, they are fairly stable. I mean, they're pretty stable, but sometimes you may have to reboot the machine too. I mean, sometimes when you it's not supposed to happen, but you are going a little bit further than your usual C program, right? So if that happens, just reboot and start over, right? That shouldn't happen, If you have the proper fuse library, it shouldn't happen, but we know how that goes, right? So we can continue back with the file, files and directories and stuff, and we're kind of falling back, and that's fine. So essentially, we in the last lecture we stopped off with, we were trying to figure out how to do allocation, block allocation, and it's a lot similar to what you would do for memory pages. You can allocate in different sizes or block sizes. Most of the file systems offer in block sizes, fixed block size, which means that you have internal fragmentation, no external fragmentation. So the next key is, how much do you give, right? So I can give you, if you ask for each block, I can give you one. The where we left off last time was on contiguous allocation. So when you start up the file, I give you all the blocks you need, and it's kind of harder to grow. The idea here is you don't want to go to the operating system every time you ask for a block, right? So if you don't want to go all the time, you can have we start off with extent-based system, which is a kind of compromise. So you go to the operating system, ask for an extent, which let's say is a megabyte. So you ask for a megabyte, and if you want more, you ask in megabyte size chunks, even though the block size are smaller, right? So you end up wasting a lot of space but you don't have to go to the operating system as much. So if you're working on a high-performance file system, that's something that you may want to do. The less you ask the operating system, the faster your program potentially could be, right? And of course, you waste a lot of space, but if you're talking about a big file server, you may not really care, right? So the other way of doing stuff is through linked list, right? Essentially, for every block you have it points to you have to point it to the next block that your program will need. So the nice thing is you have one address, and I can chase that to figure out all the blocks, right? So if I open a file, I get one pointer, and I read that block. That block tells me where the next block is, and which tells me where the next block is, and so on and so forth. So I have one pointer to figure out all the blocks in my file. It can grow to whatever size it wants, right? The bad thing is I have one pointer, so I can't just randomly jump to some point, right? If I want to jump to a particular offset in the file, I still have to chase down all these block pointers, right? So, start off, like in a directory for a file Jeep, you have a start of block 9, and block 9 says the next block is at wherever, right? So it should go to 1, right? 9 should point to 1, but it points to 16. Hey, but you get the idea, right? It has to point to the the pointers are way off, right?
Is it -1 right now?
Yeah, that's the end of file.
The second digit got cut off.
Yeah, okay.
That's what happened.
Yeah, so the second, one digit. So essentially you get the idea, right? You trace these pointers. So if you want to go to block 4 in the file, you have to read the 1, 2, 2, 3, and 4. Yeah.
You don't have random access within a block, though, still.
Yeah. You do have random access within the block, right? But yeah, if you want to go beyond the block, you have to do that, right? You have to chase these pointers. Right? So this is essentially what DOS fat file system does, right? It's simple because it stores the start block. Essentially, you have to chase down these blocks to figure out where the rest of the file is. It can grow to whatever size you want because you're essentially doing this, right? But it's slow, but DOS was not designed to be a super fast file system, right? What other problem do you see with this approach? One of the things you worry about in file system is corruption, right? If you corrupt some pointers, corrupt some data, in the memory case, your operating system will crash, right? If you have something messed up in your OS kernel structures, you will crash, right? Which is bad enough, but when you reboot, hopefully you'll be fine, right? Whereas in a file system, you mess up, it's there forever, unless you go and fix it, right? And that's something that you have to keep in mind. So all these things are presumed to be there for forever. And so in this case, if one of the blocks get corrupted, you lose a whole bunch of stuff. So for example, if you point to 217 and the pointer, if that block gets corrupted, right, the block which points to 618 gets corrupted, then essentially you have no way of knowing that these blocks exist, right? And we will see from the free block component, which is the next one, we'll know from the free blocks that these are not free, right? We'll know that 618 and the bottom 2 blocks are not free because it's not on the free block entry, right? So now we have a file where you can't connect that file to the rest of the blocks, right? You lost this pointer which says 618. So you have a bunch of blocks which are hanging around, which are not in the free block, which no one is pointing to, right? So you don't know which file it belongs to, but they are just there, right? So any of you remember doing scan disk, right? In the DOS world, you have to do the scan disk. If something happens, you pull the plug without properly shutting down the machine, right? It'll do the scan disk, and it'll create these files called scan. I forget what it is. Scan disk.000, scan disk.111. It creates a bunch of files, right? Have you guys seen those? It creates a bunch of files in your main directory, right? And those are essentially files it knows. So it has these 2 blocks. It has a block from 339 pointing to the last 2 blocks. Nothing is pointing to it. So this is a chunk that belongs to some file. but you don't know what it is because nothing is pointing into it, right? It knows it's not free, but it doesn't know who it belongs to, right? So those go into the scan.0 file. It's up to you to figure out what to do, right? And that can be pretty annoying because you have, if it's a text file, you could kind of make sense. If it's a binary file, it's completely lost, right? So you have to weigh in those factors, and and figure out what you want to do. So in terms of performance, this is not exactly a screamer because you have to read all these blocks to get the random access. So then the next model is to do a index, which is sort of like a directory, right? Here you have an index which tells you where the blocks are. So if you think of that as an abstract, like an array of pointers, you would say the first block points, where the first block is, second block is, and so on and so forth. So you have a directory of all the blocks. So depending on how big the index table is, your file can be so big, right? Your index table can have 1,000 entries, and if each block is 1,000, then your file can be at most 1 million, right? So essentially you have these pointers going through, right? So if you lose the index table, then all is lost because then you have a bunch of blocks. You don't even know which order they should be stored, right? So essentially, if you look at it from the index block, it says is 19. So 19 points to a whole bunch of stuff, right? So 19 says the first block is at 9, second block is at 16, third is in 1, fourth is in 10, fifth is in 25, and a whole bunch of negative ones, meaning those are not, the file is not as big, right? Again, depends on how big the index block is. And then you can still get random access because you read the index entry, then you know whichever block you have to go, right? Essentially, you read the index entry once, and then you know where your data block is, right? So in this system, you have to first read the directory block, then you have to read the index block, then you have the file, right? So you're paying the cost twice. First to read the directory, second to read the index block, third to read the actual block. And so again, it depends on how big the index block is. And the little math we said, the file can only be 1 megabyte, right? And remember, all of these things have to be in a block boundary because that's how the disk is operating. So rather than making the index block itself span multiple blocks, you like the index block to fit into one block, right? So if you do that, then it restricts how many you can achieve and stuff. So depending on the block size, you may be able to address a larger file or what have you. The way you solve that is to have a hierarchy of indexes, right? So in this model, you have an outer index and the inner index. So you're creating a tree, right? So you have an outer index pointing to an inner index pointing to the actual data blocks, right? So in this model, you read this index, right, which tells you where the second index is, and you read that to figure out where the block is, right? So you have to read the directory entry, this block entry, this entry to read your contents. So you have to read 4 times to get to your data. You get random access because essentially you can access anything by going through this hierarchy, right? And that will exponentially increase how big your file can be, right? So you can keep increasing to how much you want, right? So this is a way to have a larger file and still be able to access all the blocks, right? And so doing this will make you pay the cost for every block. So every block has to go through these indexes, right? So what Unixes do is they made the observation that most files are small, right? So if most files are small, there's no point in making the small files pay all this cost, right? So what they have is a multiple levels of indirection where in the classical Unix, and this may have been enhanced a little bit, the first 10 blocks are direct blocks. So if you look at the direct, so if you have the file entry, the file inode entry, it's called the inode, right? The first 10 blocks point directly to the data. So when I open the file, I know the addresses of the first 10 blocks from my directory entry, right? The next one block is one level indirection, right? So the next one block is you have the directory entry pointing to the data block, right? This is the data block. you have from the single indirection you point to the index block to here, right? And the next one entry is double indirect, and the next one is triple indirect, right? Triple indirect would point you to one of these, pointing to another one, pointing to another one, pointing to a data block, right? So as your file size becomes larger and larger, right, once you start seeking to the very ends of the file system of this file, right, and depending on the block size, it can be up to 4 gigabyte, right? So if you are seeking to the 4th gigabyte position, you would have to read the first triple indirect block and then chase it down to read all the indirect blocks. So your performance will only be slow for larger files. Smaller files get to up to 10 blocks don't have to do this index block reading, right? And that's how they. So again, there's no magic here. This is basically based on observation that most files are small. So rather than making them play a uniform cost, you have this weird data structure where the larger the file is, the performance changes, right? And of course, then you know, all this depend on the size of the block, right? So if the block size is smaller or larger, you may be able to have more direct blocks, right? So if it's larger, you can have more direct blocks. And depends on the pointer size, right? The pointer size, if it is 32-bit or 64-bit, right? If it's 32-bit, then you can have more blocks in the direct block entry. But if it's 32-bit, your file can only be 4 gigabytes max, right? So if you want larger files, then you have fewer entries and stuff. So you kind of, so the choice of the block size, the choice of the pointer size decides how big a file is and how many entries you can have, right? Again, you have the same problem. If you lose any of these pointers, you're in trouble, right? If you lose any of these, like for example, for the third index block, if you lose the block which has the first index block, then you lose a whole chunk of data after that, right? So that brings up a notion of the free block, free space management. How many of you finished with your homework project? How many of you started? And okay, a few of you started, right? So yeah, I mean this one can actually have more programming involved, right? So I suggest you start as soon as possible. So essentially the notion here is one of the things that you'll do in your project is keeping track of which blocks are free and which blocks have been allocated, right? And again the notion here is all the structures have to be on the file system, stored somewhere. It can't be purely on memory because, like I said, the storage system can crash and be brought up some of the time. So you have to keep all the structures on the disk. So you have to make sure that all this stuff are also on the disk. So in memory, you can have a bit vector, right? So you can keep a vector which says whether a block is free or not. So depending on the file system size, you create a big bit vector, right? So if you say this bit is 1, that means it's used. If it's 0, it's not used, right? And it doesn't have to be long, right? So for example, if you have a block size of 4 kilobytes and a disk size of 256 gigabyte, right? Essentially, you have to figure out what the n would be, right? If you divide those two, you get 8 megabytes, right? So you have an 8 megabyte long free bit vector for managing the free blocks, right? Which has to be stored on the disk, which has to be read back. And essentially you can, so that means you have a count of all the disk blocks which are out there, right? All the disk blocks you have an entry. So the corresponding entry is 1, it's being used. If it is 0, it's not being used, right? And you have to manage this thing. And I think in a slide or two, we'll see what's the tricky part in managing these things, right? Essentially, the tricky part is you expect this to be accurate, right? If this is not accurate, things can be bad, right? So what happens if this entry shows a 1 where it's really 0, right? Meaning what happens if the storage system thinks that a block is being used, but it was really free? Yeah?
Space is wasted.
Yeah, space is wasted, right? Space is wasted, and since the file systems exist forever, if you assume it exists forever, right? As time progresses, if you keep adding, if this keeps happening at 1 block a day, something, right? Eventually, you lose a whole bunch of space, right? What happens if the other way happens, right? Where it shows it's 0, and it really should have been 1. Yeah.
You may overwrite space that you're using for a file.
Yeah, you may allocate the same block to 2 different files, right? 2 different files now have pointer here. So this block, file 1 thinks it's file 2 thinks it's its own space, right? Depending on what they do, if they write or read or whatever, you'll see another one, right? This is not sharing because this is unintended. Yeah.
In the first case, how do you fix that? Do you have a block that it should be free, but
so how would you fix that?
Well, in the linked list example where we had previously, we had like a pointer to an Xbox. I guess you could sort of follow all your files through the pointers down to their child nodes. And if you have one, I don't know if you have blocks about that.
Yeah, that's an excellent way of solving it, right? Essentially, you read all the files in your file system, in all the directories, read them from start to end, follow all the keep marking all the pointers, and if particular block, so you know what the file system thinks, and you know what the free block thinks, and then you can reconcile those two, right? Which is essentially what your scan disk, FSAK, whatever operating system you use, whatever way it does that, right? And it's an extremely slow operation, right? Because you're reading every single block in the file system, right? So for people who have used FSAK, for people who have done scan disk, right? You must have done scan disk on Windows because it used to do quite a lot, right? And the Unix variant is FSAK, right? And they both take a while, right? I mean, they don't take a while if the file system is pretty small. I mean, you probably can get by. But for like one of my lab machines, like a 500 gig machine, it takes like 3 or 4 hours, right? Because it has to read all the stuff, right? So it's painful, right? So you don't want to do that unless you have to, right? So you don't really care about the first part where you waste space. You do care, but it's not as catastrophic as the second case, where your 2 files are linking to the same block, and that could be pretty bad because this is unintended. So your program or your systems can crash, right? So for example, in the worst case, they both could be pointing for the kernel, right? In which case your kernel won't even boot up because it has a corrupted file, right? But it won't know it's corrupted because it says that block belongs to me. It doesn't know some other file also points to it, right? So that's the problem with keeping those things, right? So essentially that's what this slide talks about, right? So when you allocate a space, when you allocate some block, you have to mark it on the free block, right? But you have to make sure that it's written onto the disk, right? Because if you don't, then you could get into the second case, right? So you would rather have the first case than the second case, right? So what you do is, when I allocate some block, I write that entry onto the disk, right? You don't have to worry about this for your homework project, but so in any allocation scheme, I allocate a block, I write it to the disk, right? Then I actually give the block to the other process, so make entry on other processes file system, right? So if it crashed after the first part, that means in your disk it thinks this block is allocated, but in reality it was not allocated because it was not actually given to the next process, right? So I freed up a block. I was going to give it to a file, right? And then I'm going to do something. So first I marked on the disk that this is no longer free. Then I give it to the file where it can write it. It can create whatever data structure. If I crash between these two, then I get into the first case, where on the disk it says the block is written, it's allocated, but actually it's not allocated to anybody because the second step I couldn't do, right? So I would rather have this than the first case, than the second case, where 2 files are pointing to the same thing. So then I set it in my memory, so I can progress with that stuff. So at this point, if I crash, then this block can be wasted, and you can go through this scan disk or whatever at some point to reclaim those. But for now, you're safe, right? worry about safety more than wasting space. Right? Make sense? Yeah.
People who have Windows XP, should we run ScanDisk every month or so? Or what do you idea?
Windows XP is, if you use NTFS file system, it's a lot more robust than these.
Okay.
Right? So this is the DOS. It's easy to explain, easy to understand, but it has too many issues, right?
Okay.
And we'll see a little bit how the disks are organized and stuff, and the notion of Windows. What do they call it? Like they rearrange all the blocks to
Defragment.
Yeah, defragment, right? And we can see what that means and whether they are necessary, right? In a few lectures, right? So essentially, so that's keeping a bit vector. The other way to do that is to follow the same way as we did for the DOS file system, have a linked list, essentially, which you keep a linked list of all the free blocks, right? So I keep one entry, and you read those, read the pointers to see which blocks are free, right? And it fits in perfectly with the DOS fat file, right? Fat file, for the files you have this pointer. Now you have one more pointer for free blocks, right? If I lose the head, then I'm in trouble. But otherwise, it's as robust as the other component, right? So those are the two ways of maintaining and keeping track of the free blocks, right? So all these in essence, what we are glossing over is the actual performance impact of any of these schemes, and those depend on what types of files you're accessing, what's the block size, what access patterns you're seeing, right? So, for example, in the DOS file system, right, if you're accessing a file sequentially, meaning you start reading from byte 0 all the way to the end of the file, right, you won't notice any difference, right? Because essentially, since you're reading block by block for useful purposes, I read the first block, I know the pointer for the second one, and I keep going, and so on and so forth. But if I do a lot of random access, then all these things become a issue, right? And if I'm reading small files, then the Unix system it's fairly good, right? The worst case would be if I'm doing a lot of random access at the very high address, right, at the very end, right? So then I have to read a whole bunch of the third-degree indirect blocks, right? So it all depends on what you're trying to do. And the reason why file systems don't really suck bad is you have to have caching, right? If you don't have caching, if you have to read from the disk, right from the disk, these 3-level pointers would kill you because you have to wait for reading from the disk every time. And reading from the disk is slow. I mean, we're talking 10, 20 milliseconds to get each block, right? So if you're doing 3-level indirect reading all this time, you'll noticeably notice things being slow. And so you have to keep as much cache as possible. And I kind of alluded to it last time. The more memory I give you, right, I can give it to processors, I can give it to your programs and stuff, but if I give memory here, then it's wonderful, right? And managing this cache is a problem. I don't have infinite storage. I have to keep track of which ones to throw and which ones to keep, right? So in this world, I can do read ahead. Remember, we did some of this for the paging too, right? If I know that you're going to be needing a block in the future, I can read that block before you come there, right? And I can free some blocks sooner if I know what you're doing, right? So for example, if you're doing a sequential access, if I know that you're going to do a sequential access, right? Which means that if I read byte 1, I know you're going to read byte 2, right? Or let's talk in block, right? If I know you read block 1, I know you're going to read block 2. Then I know you're going to read block 3. Then I know you're going to read block 4, right? If I as operating system know that, then when you ask for block 1, I can start reading block 1, block 2, block 3, and so on, right? So that way, when you come to block 2, you have the data, right? More importantly, I know that you're going to go from block 1 to 2 to 3 to 4. So when you go to 3, I can get rid of 2 because you are not coming back, right? So you're going forward, so you're not coming back. So I can free behind me, right? So this is not LRU. This is the most recently used kind of thing, right? So I know you just used 3. You went to 4, so I'm going to get rid of 3, right? So all these things are possible because I know how files depending on if I know how the files are being used, right? So there are a lot of studies trying to figure out how people use files, right? And for the most part, at least on the Unixes, people tend to use files sequentially, start to end, right? They open a file, read all the contents, and then they close the file, right? So they can assume that that is what you're going to do for most part, right? And if you think about it, it's not pretty bizarre, right? So if you work on a Unix machine, you compile your program, right? So the compiler has to read your program from start to end and do whatever, right? So once it's compiled your program, it gives it to the next stage, and so it writes all the contents to the file. The next stage reads all the contents back, right? You edit your program, your editor, so it reads all the contents and it writes all the contents back. So they're all sequential, start to end kind of model. So OSs can pretty much assume that's what you're going to do. They can optimize for that, right? And that's one of the reasons why you may want to push the database into the operating system, because then the OS can say, you're operating on an index-based operating system, so I have to optimize it for you, right? But so there are ways to do this stuff, and these allocation may not be what we did for the paging stuff. It may not be LRU based or what have you, and it depends on what the accesses are, right? And one way to do that is to improve the performance using your memory itself as a disk, right? Many of the modern operating systems tend to do that, where they notice that there are certain files which are created often. They created and then erased often. So rather than putting them onto the disk and paying all the price, if you have enough memory, you can create them into this RAM disk, right? Where it's not persistent, it looks like a disk, you write into it, and then you can read from it. It's pretty fast, right? So one of the examples I was just mentioning, right? Most of the when you use a compiler, right? When you use let's say GCC, right? So first it does a pre-processing stage, then it does the compilation stage, then it does the assembly stage, then it gets a linking stage, right? This is typically how your program goes, right? So first, if you see .c, it creates a .i file, and it will create a .s file, it create a .o file, and then create a executable file, right? You usually have this as a program, 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 right? Your C file comes here, it writes a file, and this reads a file, writes a file, reads a file, writes a file, reads a file, and gets out, right? This is one way you can do that. You can either pass it as a pipe or write it into a file and all those things, right? So if you look at this model, these files are not really files. These are ways for this process to communicate its contents to here, right? They should somehow give the contents over here, right? So rather than putting this into a disk, if you put this in a RAM disk, it essentially goes in memory from here to here. Even though it looks like it's a file, it's not a file, right? If the machine was to crash, this file would be lost, but that's okay because no one knew that this file was being created and so on, right? So, yeah.
So the temp file system is usually used by like low-level utilities,
yeah,
like the compilers. So
you can use it for your work too, right?
Okay. So is that just like, is that the directory is /temp or?
/temp can either be /temp in the file system, or it can be as a RAM disk, right? Typically, you put /temp as a RAM disk, right?
Okay.
You would not put a home directory in RAM disk because then when the machine crashes, it's gone, right? But for performance, so it depends on how much memory you have. If you don't have enough memory, you don't want to do this, right? But if you have too much memory, you can put them as a RAM disk, right? So this is one component which was left over from the memory allocation mechanism, but it actually really belongs here, right? So the idea here is, this is pretty nifty, right? If you think about it, when you think of the memory virtual memory system, right? Virtual memory had this chunk of memory, right? And it couldn't keep all of them in memory, so it put them on the disk, right? So depending on what pages you wanted, it brought them into main memory, did some operations on them, and when it didn't have enough space, it put them back into the disk, and it brought something back, right? So the paging system essentially was moving stuff back and forth between swap space, which happens to be a disk, and only bring contents when it needs to be, and then it throws it back when it doesn't want it to be, right? So your OS actually does that. I mean, it essentially brings only the pages it wants and then moves the disk contents where it doesn't want, right? Since it's doing that stuff, right? This is disk, right? And it's just memory it's automatically managing. And when you think of it as a file, right? It's the same thing. It's in some disk, right? And you're operating on some blocks. So why do we have to do this open, read, write, and close, right? The file system operations, right? If you can use the same virtual memory stuff here and say my file is in this area to this area on the disk, virtual memory system, you take care of it. I will access it any which way I want. You bring it in whichever way it suits you, right? Bring the disk into memory where I have to modify, and you write it back whenever you choose to, right? And that's the notion of a memory map file. You have a file, I memory map it into my program, then I do any modification. Virtual memory system, the way it did before, which is move the pages whenever it wants to from disk or memory whenever it wants to, and I get to use the virtual memory system to get good performance, right? So in this way, I don't have to do read write anymore. I just have to access it as memory, right? And I think it's really cool. So I have a real program. So essentially, once you do this, all the pointers, it shows up in a virtual memory. So let me show it as a program, right? How many of you actually use memory map files explicitly? Because most of your libraries, C libraries, do this without you knowing about it, right? So you have used it without actually knowing about it. So let's look at explicitly how you do it, right? So again, I have the same program which we looked at before on how to create a file, right? So I open a file. There's nothing new here. So I open a file, I create a new file, and then I write hello world into it. So the contents now is right. This is what the file has, right? This is the stuff from before, right? And since I'm accessing as a file, I have to do open, I have to do a write, I have to do a write, I have to do a close. I can use seek and all those things, the special file system calls that I'm used to, right? So when I want to do it as a memory map file, right, the first thing I have to do is create this memory map, right? And it's kind of yucky code, but essentially it says that I want to memory map. Ignore the first address. I mean, that's a more specific thing. It says that I want it to be mapped at a particular location. Here we don't care, so we leave it at that. We say I want to map 4 bytes of memory, right, from this file, and I want the protection to be read and write. I can also have execute, right, and you can do a whole bunch of cool stuff with the mmap, right. For now, we have to say I want the memory region to be read or write, right? And I want it to be mapped shared. So 2 processors can share into the same object. And the file descriptor I want to operate on, the file I want to do is the file descriptor, which I opened over there. And 0 is the offset in blocks, right? So with this, what I'm saying is I want the pointer to now point to, in virtual memory, an address starting from here. And I want it to be 4 bytes, right? So from here to here, I want it to show up to me in a virtual memory as a memory address, right? So I mapped this file starting from address 0 for 4 bytes in read or write mode to the particular backing file, right? So when I do pointer equal plus 2, so I'm pointing here, right? And when I copy, actually that code, I only, yeah, there's a little bug, right? I only mapped 4, right? So you see, I should be able to write 3, right? So yeah, let's make it 2, right? Which means that in my memory, I write LP. Actually, it's a map 5, right? So I want this to be blank, right? So I unmap the file, right? So when I close the file as a file, your actual file content would now be help like this, right? So this is a cool way to access the file. So you can do whatever you want here. You can have pointers and all the stuff in here. So you no longer have to worry about the read, write, and other file system calls. You operate all of them on memory calls. And what you're really doing is, since we know how to do virtual memory from previous module, I'm just asking the virtual memory module to take care of my file, right? I know virtual memory module can deal with bringing pages from the swap disk and putting it back. Instead, rather than doing from swap, do it for my file, right? And I don't have to worry about when to write, when to close, right? So in this case, I may be doing copies many times, right? When it has to go to the disk is not up to me, right? So for example, if I write a code, let's say I do a lseek to 2. Can you see? I just go on a loop and then I seek to location 2 and write 1 byte, right? For some strange reason, let's say I'm doing this, right? And the other model would be, I say, let's say, right? The memory map version would be, I go to this address. I'm not going anywhere else. I'm keep writing here, right? I could be doing this. Right? These two are equivalent because here I seek to here and I write, seek, write, seek, write, seek to the same location, I write 1 byte, right? Here I'm not going anywhere, so I have, I'm keep writing here, right? In this case, since I'm explicitly saying seek and write, each write will have to go to the disk or whatever. I mean, I'm taking controls. I'm expecting it to do a disk or what have you. The operating system can do some tricks for me, but I'm explicitly saying these things should happen. Here it happens implicitly, right? So if you go back from the memory simulation homework project, right? This need not translate to anything at all on the disk. If you have enough memory, your virtual memory system may not write anything into the disk at all. So this may ignore a whole bunch of disk writes and reads, right? So performance-wise, this may actually be a little bit better, right? But also, there's no notion of flushing, right? There's no notion of saying it has to be on disk, right? Because now you're completely trusting the virtual memory. So whenever it chooses, it can put it onto the actual disk, right? Which may or may not work to your advantage. But it makes your program either a lot simpler or a lot harder, right? Yeah?
Like if you're doing some kind of debug output or log file, see the progress, you might not want to use the second method because if your program stopped unexpectedly, it might not even flush.
Yeah.
Is there any way you can explicitly say
no,
flush everything you
no. No, you can't flush, right? There's no notion of flush because it's memory, right? No, you can't do that. I mean, yeah, you can't do that, right? But the nice thing is you can actually have pointers, right? So if you mapped all this stuff, you can actually have a pointer pointing to here, right? Which you can access as your C pointer, right? If you have this as a structure, you can say the pointer pointing to here. So the whole file can be treated as a pointer data structure, which essentially goes into the disk as pointers, right? Which can also make your program pretty hard to debug if some things go wrong because it's a memory dump of what you have, right? Yeah.
Just to make sure I understand this correctly, with your unmapped data call, with your unmapped function call right here, shouldn't you have pointer -2 because you added 2 to pointer originally?
Yeah. Yeah. It should be. Yeah. Yes. Yes. Yeah. It should be. Yeah. I messed up the pointer, right? So. Yeah, it should be pointer minus. After the mmap call, I say pointer plus equals 2. So pointer now points to +2. So I'm unmapping 2 bytes which I didn't have, right? All this code went through because memory map happens in block boundary, not on offset boundaries, right? So even though I said I only want 4 bytes, it's a block. So everything fits into a block. So, and the offset at the last one is in blocks, not in bytes. So when I say offset 0, it's not 0 byte, it's 0 block, right? Because now you're dealing with virtual memory. Whatever virtual memory gives you is what you have. So the block size is not your file system block, but your virtual memory block. So there are system calls to figure out what the current operating memory block size is, and you have to use that, right? So your program gets a little bit more tricky because you have to deal with memory blocks, and you know, you can't flush it whenever you want to and stuff. But if you're a database and you know what you're doing, this may be a way to keep things simple, right? It's a judgment call, right? Whether it's easy or not, right? And the thing is, once I have this pointer, I can give it to any other process. So I can give this to a printf, or I can give it to anything else, and they don't know whether this is coming from memory mapped or not, right? And that's why I'm saying, like, for a lot of your C system calls from a library, they actually do a memory mapped I/O for your files, and you don't know it because you get a pointer. You don't know whether the pointer is, you know, memory pointer or a memory map file pointer. Right? So that brings up the issue of the caching and how we manage this stuff. So page cache is the one we were looking at from the previous module, which is for every memory page. You can have them in cache, right, from main memory onto your cache, and so on and so forth. Whereas the file system operations operate on what is called buffer cache, which is a I/O cache, right? It's all the same main memory, but depends on how you access them, right? So virtual memory system typically uses its own page cache, and file systems uses its own buffer cache, the same memory in different fashion, right? And that comes about because the development happens similar to what we did in the course module, right? So we looked at the memory system separately in last module. We're looking at the file system now, and the first generation of operating systems typically tend to have something like this, right? So you have a file system, and it goes through a buffer cache, right, where all the contents, your directory blocks and all those things are read and cached, and that are operated upon by I/O operations, right? And these buffer may also be, once you go to the virtual memory system, virtual memory system has its own way of caching, right? It won't affect you anywhere at all, except if you start using memory map file, because then memory map file would be using the VM's notion of caching and your file system's notion of caching, which means that if you open a file and memory map one process memory maps, other process reads and writes, then you'll have unknown behavior, because the one which opens read write would be operating on the buffer cache. The one which is operating through the memory map would go through the paging cache before it gets to the buffer cache and onto the disk, right? Does that make sense? Right? Imagine the previous section, right? The previous section was only operating on its own cache, right? That was called the page cache, right? And now you have another cache which is being operated on by the write system, which the other one does not know anything about, right? The virtual memory system assumes that it's managing its disk and all those things. It does not know somebody else is managing these things. So you can run into these weird cases where there are two caches and you get inconsistent results depending on how these things turn out. So the idea here is to unify them, right? Actually have a unified buffer cache where there's one cache, it's used by the virtual memory system, it's used by the file system, so everything is solved, right? It sounds trivial, you know, because we just have like a bunch of blocks here and say unify this is fine, but it's not as trivial because now you have two different functionality, you know, the memory system and the file system using the same cache, right? Which means that these two people have to come together to use the same mechanisms, same buffer. And if memory system is using this, you know, the caching, it'll conflict with what the file system wants, right? The allocation goes to a single point and stuff. So that means that makes your operating system a lot more complex, right? There are two different components wanting to use the same cache. They both have to use the same free mechanism, C allocation mechanism. The memory stuff happens faster, this stuff happens slower, but they're all fighting with each other, right? And if a page has to be evicted from the memory side, right, it has the same precedence as the disk side. One of them is slow, one of them is fast, kind of thing. We'll talk about this in the next module on how these things matter. But if you remember, the memory is much faster than the disk, right? Now you're mixing both, so you're making the same decision for both of them on which one to evict and stuff, which may or may not be good, but that solves some of these problems, right? And we'll continue with this on the next lecture. But we have the exam on So we have the test on Wednesday, but I'd like to, like after the exam, take 15 minutes to finish up some of the contents, right?